If you spend any amount of time working with large language models, you've probably noticed this one really specific quirk.
Oh, the absolute refusal to admit they don't know something.
Exactly. Like when it doesn't know the answer, it never stutters. It doesn't, scratch its virtual head or admit defeat. It just lies to you with this absolute terrifying confidence.
Yeah, it'll just invent historical battles out of thin air.
Right. Or fabricate legal precedents, or insist that a pound of feathers is heavier than a pound of bricks. And it does it all while maintaining the authoritative tone of, like, a tenured professor.
It's wild.
Yeah.
But that's actually the focus of what we're looking at today.
Yeah, so welcome to today's deep dive. We are taking you through a brand new piece of state-of-the-art research that might finally teach artificial intelligence how to, well, doubt itself. Because, we want you to get a quick but thorough grasp on the cutting edge of Gen AI without drowning in all the academic jargon.
And this is arguably the most critical bottleneck in the entire field right now, because we are slamming into what researchers call the data wall.
The data wall, right.
Yeah, for the past decade, we've just been feeding these models on a diet of human-curated information, right? Scraping the entire internet to teach them how to reason. And we're basically running out of high-quality human text.
So the obvious next step, and I mean, we see this everywhere in the industry right now, is self-evolution. Like, if we humans can't provide enough data, the AI just has to start generating its own practice problems, answering them, and then grading its own homework.
But that brings us to the core mission of today's deep dive. Because when you ask a machine to grade its own complex reasoning, you run into a massive mechanical failure.
Right, which brings us to the source material. We're exploring a paper titled Confidence-Orchestrated Self-Evolution Against Uncertain LLM Feedback. And this is from researchers at George Mason University, including Bowen Wei alongside Nan Wang from Amazon. And they've built this framework called COSE. That's C-O-S-E.
Yeah, COSE. And to really grasp why COSE is such a paradigm shift, we kind of need to look at why current self-evolution techniques are, failing so hard.
Okay, let's unpack this. Because I know supervised fine-tuning hit a scalability wall. You just simply cannot hire enough human PhDs to write millions of flawless, multi-step logical proofs.
Right, it's too slow and way too expensive.
Yeah.
So the industry pivoted to reinforcement learning with verifiable rewards, or RLVR.
And that works incredibly well for like certain specific domains, right? Like coding.
Exactly. If you're training a coding model, the AI generates a Python script, and you just run it through an external compiler. That compiler is a definitive verifier. The code either executes perfectly or it crashes.
It's black and white, very binary.
But the moment you move away from executable code or like rigid math formulas, and you try to teach a model open-ended reasoning.
Like philosophy or strategic planning.
Yeah, exactly. The external verifier just vanishes.
Yeah.
I mean, you can't run a philosophy essay through a Python compiler.
No, definitely not.
So the model has to act as its own judge, generates an answer, and then it's prompted to evaluate its own logic. And this is where the optimization catastrophe really begins.
Because when a model generates noisy or incorrect feedback on its own work, it isn't just like giving itself a bad performance review. In a reinforcement learning setup, those bad judgments become erroneous gradient updates.
Right. And if we connect this to the bigger picture, a gradient update physically alters the mathematical weights inside the neural network.
Yeah, so think of it like a struggling high school student grading their own advanced calculus exam. If they fundamentally misunderstand the chain rule, they might look at a completely flawed proof they just wrote, confidently mark it with a big red check mark, and feel this huge surge of validation.
They're practicing how to be wrong.
Exactly. They aren't just making a one-time mistake. They are actively burning that flawed mathematical rule into their long-term memory.
And the fallout from that is this incredibly destructive feedback loop. Because false endorsements, where the AI judge approves a bad answer, they reward flawed reasoning pathways.
And then you have false rejections too, right?
Yeah, where the judge throws out a brilliant, creative solution just because it doesn't understand it, so it discards highly valuable supervision. Over repeated cycles, the AI actually amplifies its own hallucinations.
It bakes its own cognitive blind spots deep into its core architecture, which is exactly the crisis the researchers from George Mason and Amazon are trying to solve with CSE.
Yeah, and their core premise here revolves around extracting what they call an intrinsic confidence signal from the model.
Okay, so they're arguing that we shouldn't treat all AI-generated feedback as equal. We need to measure how confident the LLM actually is in the exact moment it's acting as the judge.
Right. And the mechanism they use to capture this is fascinating. They measure confidence using something called token-level normalized entropy.
Okay, token-level normalized entropy. That sounds intense.
It sounds heavy, but to visualize it, you just have to think about how an LLM actually generates text. I mean, it doesn't think in complete sentences. It predicts the next tiny chunk of text, a token based on a massive probability distribution across its entire vocabulary.
So if the sentence is the capital of France is, the probability for the token Paris is probably sitting at like 99.9%.
Exactly. It's a massive spike on the graph. That is a highly concentrated probability distribution. So in mathematical terms, the entropy of that distribution is extremely low, which means the model's intrinsic confidence is sky high.
It's like a spotlight shining directly on one specific word.
Perfectly said.
Hmm.
But contrast that with a scenario where the model is fundamentally confused. The probabilities might smear across the vocabulary, like maybe 10% for one token, 8% for another, 12% for a third.
So it's no longer a spotlight, it's more of a dim floodlight.
Right, the distribution becomes uniform.
Yeah.
And when that happens, the entropy spikes. COSE continuously calculates this entropy across the entire sequence of tokens the model produces while writing its feedback.
And it aggregates that mathematical messiness into a single confidence score between 0 and 1.
Exactly.
But wait, I have to throw a flag on the play here. Because we started this deep dive by talking about how AI lies to us with absolute certainty. Like, I've had models argue with me about basic physics while sounding completely authoritative.
Oh, we all have.
Right. So if the AI can hallucinate confidently in its text, how can we trust its internal probability distribution to guide its learning? I mean, doesn't a confident hallucination just look like a low entropy spike?
That is the most crucial distinction to make regarding the entire COC architecture. The researchers are very clear that they do not use this confidence score as a formal guarantee
Right.
of truth. Yeah, token entropy is not a lie detector. It is purely a lightweight uncertainty signal. Think of it as a damage control mechanism.
So it's essentially a failsafe.
Precisely. If the model is visibly wavering at the token level, like if the entropy is high COSE, simply tones down the training impact of that specific piece of feedback.
It doesn't mean highly confident answers are always factually correct. We know they aren't.
Right. But it does mean that when the model's internal math shows it is actively guessing, we absolutely should not use that unstable judgment to drive a massive, permanent update to the neural network's weights.
Okay, that makes a lot of sense. But seeing an AI recognize its own wavering confidence completely changes how we have to look at its architecture during training, because the paper mentions that a single model is essentially split into different components.
Yeah, the framework actually forces a single checkpoint to adopt 4 distinct personas through prompting alone:
4 personas.
a proposer, a validator, a solver, and a judge.
Hold on. You're saying one single AI model is playing 4 different characters simultaneously inside its own training loop. Isn't that just a snake eating its own tail? Like, how does a single neural network separate those roles without just bleeding them together?
Well, it's all about context isolation. The model isn't talking to itself in one massive, confusing thread. It's run in separate, isolated inference passes. So first, you prompt the model to act as the proposer, generating a brand new candidate question. Then, in a separate isolated instance, it acts as the validator, evaluating whether that generated question is actually logical and solvable.
Got it. And then the solver steps in to try and answer it.
Exactly. And finally, the judge reviews the solver's work.
Here's where it gets really interesting, because the actual learning mechanism here, the way the weights are updated, relies on proximal policy optimization, or PPO,
Right.
which is a method designed to take very small, calculated steps. Instead of overhauling the AI's whole brain at once when it gets something right, PPO updates the policy just enough to improve while staying proximal or close to its previous state, to avoid accidentally breaking what it already knows.
And the brilliance of COSE is how it orchestrates that PPO update across these 4 roles. Because the optimization, the actual rewiring of the neural network, only happens on the proposer and the solver.
Oh, interesting. So the validator and the judge don't get their weights updated during this loop.
Nope. They are frozen in place just to provide inference time feedback. Their token-level confidence scores simply dictate the magnitude, the sheer weight of the PPO updates applied to the solver and proposer.
Okay, I need a concrete example to ground this because the abstract mechanics are getting a little heavy. If I give this 4-headed AI system a problem, how does that entropy signal actually step in to stop a bad PPO update?
Well, the researchers provided some excellent test cases in the paper to illustrate this. Let's look at 2 specific math scenarios they tracked during training. In scenario 1, The proposer generates a standard rate problem. A train travels 60 kilometers in 45 minutes. What is its speed in kilometers per hour?
Okay, so the solver takes a crack at it. 45 minutes is 3/4 of an hour, or 0.75. 60 divided by 0.75 is 80. The train is moving at 80 kilometers per hour.
And the solver nails it. Then the judge steps in to evaluate this solver's trajectory.
Yeah.
Now, because this is a very straightforward, high-probability reasoning path, the judge's token-level entropy is incredibly low.
The probability spotlight is laser-focused.
Exactly. It outputs an endorsement, and COSE calculates its confidence score at an overwhelming 0.94 out of 1.
Wow, okay. And because that confidence score is so high, COC tells the PPO algorithm to go ahead with the full gradient update. The update weight is near 1.0, so the model is allowed to fully metabolize and learn from that successful logical sequence.
But look at what happens in scenario 2. The proposer generates a trickier problem. A 240-liter tank fills at 12 liters per minute while simultaneously leaking 4 liters per minute. What is the time to fill?
All right, let's see.
The solver sets up the net rate correctly at first. 12 minus 4 is an 8-liter per minute gain. But then it fumbles the arithmetic at the finish line. It divides 240 by 12 instead of 8 and concludes the answer is 20 minutes.
When it should be 30 minutes.
Yeah.
So here's the exact moment where standard self-evolution drives off a cliff. Because in a normal setup, the judge looks at that flawed math, gets confused, and incorrectly endorses it. It gives the solver a thumbs up.
Yeah.
And normally, that triggers a full PPO update, burning that terrible division habit right into the neural network.
Exactly.
Okay.
But under the COSE framework, the system is actively monitoring the judge's token entropy while it types out that incorrect thumbs up. And while the judge ultimately arrived at the wrong conclusion, its internal probability distribution was an absolute mess while doing so.
The floodlight was on.
The entropy spiked massively, so COSE calculates the judge's confidence score, and it plummets to 0.31.
Oh, wow. So the fail-safe triggers. COSE looks at that 0.31 and clips the PPO learning weight down to a predefined floor. I think in the paper, they set that floor at 0.1, right?
Yes, 0.1.
So instead of absorbing 100% of that flawed reasoning, the model is only allowed to learn 10% of the lesson. It essentially says, hey, you seem incredibly unsure about this endorsement, so we're going to severely dampen the impact it has on your brain. It just dodges the catastrophic update.
And that floor of 0.1 is chosen very deliberately over absolute 0.
Oh, why is that? Well, if you clip the update to 0 every time the model is uncertain, you risk completely paralyzing the model's ability to explore new, unfamiliar reasoning pathways. You have to allow a tiny bit of exploratory noise, or the model just stagnates.
That makes total sense. So that covers how COSE protects the model from bad answers. But the paper also details how this confidence metric is used before the model even attempts to solve a problem. It actually dictates what the model chooses to practice in the first place.
Right. This is a mechanism they call confidence-prioritized replay. Because COSE maintains this massive buffer of generated questions. But pulling randomly from that buffer is highly inefficient.
Right.
So instead, it uses a mathematical formula to prioritize which questions the solver should spend its computing power on. It specifically relies on a formula represented as 4p times 1 minus p, and the variable p represents the solve rate.
Basically, how often the solver is currently getting this specific type of question right.
Okay, let me do the math on that to see how it shapes the learning curve. If p is 1, meaning the model has mastered this concept and gets it right 100% of the time, then 1 minus 1 is 0. The whole formula multiplies out to 0. It just drops to the bottom of the priority list.
Yeah. And conversely, if p is 0, meaning the model never gets it right, the formula also zeroes out.
But if p is sitting exactly at 0.5,
then 1 minus 0.5 is 0.5.
4 times 0.5 is 2, 2 times 0.5 is 1, maximum priority.
Exactly. It mathematically targets what we can call the learning frontier.
Oh, it's like a weightlifter trying to build muscle. If I can bench press 100 pounds with 0 effort, doing it every day won't make me stronger. But if I load 500 pounds onto the bar, I'll just drop it. I learn nothing.
Right. You need that Goldilocks zone.
To actually trigger adaptation, I need to load the exact weight that I fail to lift about 50% of the time. CSE forces the AI to practice in that exact zone of proximal development.
And it takes that value and multiplies it by the validator's confidence score. So it is strictly practicing questions that sit right on the edge of its capability, but only those questions that the validator is highly confident are structurally sound, and logical.
It just strips the garbage out of the practice arena.
Yeah, it's incredibly
I
efficient.
mean, the theory is really elegant. It feels like we're giving the AI a metacognitive layer. But we have to look at the empirical results. Does this actually move the needle when tested against unseen data?
Oh, absolutely does.
So the GMU and Amazon team ran COSE against 19 held-out benchmarks, tests the model had never encountered, across 4 different model backbones. They used the Qwen-3 family, ranging from the tiny zero point 0.6 billion parameter model up to the 4 billion parameter version, along with Meta's Llama 3.23b.
And the data is highly persuasive. COSE consistently outperformed existing state-of-the-art baselines like absolute zero, MAE, and R0 across general reasoning and complex mathematics.
But I noticed a very specific trend in their data tables that really stood out. The most explosive gains in performance didn't manifest on the 4 billion parameter models. The massive leaps happened on the smallest, weakest architecture, the zero point 0.6 billion Qwen model,
Yeah.
and specifically on the absolute most punishing math benchmarks, like Olympiad Bench. Why does a tiny, mathematically weak model benefit the most from this specific framework?
Well, it perfectly validates the core hypothesis of the paper.
Yeah.
Smaller models, by definition, generate the noisiest, most chaotic feedback. Their internal judges are highly error-prone.
Okay.
So the weaker the architecture, the more desperately it needs a framework like COSE to act as a guardrail against its own bad judgments. I mean, if you put a strong model on an easy benchmark, its judge is mostly correct, so a standard self-evolution loop works reasonably well.
But when you subject a tiny zero point 0.6 billion parameter model to Olympiad-level mathematics,
Its judge is constantly generating borderline, highly uncertain endorsements of completely flawed logic. By aggressively suppressing the gradient updates from those high entropy moments, COC stops the weak model from actively poisoning its own logic pathways.
so what does this all mean for other domains? We saw these massive gains in abstract math and general reasoning, but what happened when they ran COC on strict coding benchmarks like human evil or MBPP? Did it blow the standard baselines out of the water there too?
Surprisingly, no. On the coding benchmarks, COC's performance stayed completely stable. It essentially mirrored the baseline models. It didn't soar, but it didn't crash either.
And why is the researchers' reaction to a flatline result so positive?
Because it proves COSE is a do-no-harm architecture. Like we
Yeah.
talked about earlier, in the domain of code generation, you do not need to rely on the probabilistic vibes of an LLM judge.
Right, you have a deterministic Python compiler giving you feedback. The code executes or it throws a syntax error.
It's exactly. When the feedback signal is already 100% reliable, scaling the gradient update by token confidence doesn't provide any extra value. The system just defaults to standard optimization. The fact that COSE didn't regress on these coding tasks proves that you can deploy it to fix noisy natural language reasoning without breaking the domains that already possess reliable feedback loops.
That's a huge relief for developers. But to really deliver a well-rounded view, we can't just cheerlead the framework's successes. We have to scrutinize the anomalies. And there is a rather glaring hiccup in the data when they tested the models on the Trivia QA benchmark.
Yes, when they applied the COSE framework to the 4 billion parameter Qwen-3 model and ran it through Trivia QA, its performance actually regressed. It dropped by 0.11 points compared to the baseline model that hadn't used QSE at all.
A literal downgrade in performance. How does a model get smarter at Olympiad math but dumber at basic trivia?
This raises an important question, Raina. It exposes a phenomenon known as curriculum drift. Remember how the PPO phase relies on the proposer generating complex multi-step reasoning questions? Well, QOC controls how much the AI trusts its feedback, but it does not dictate the actual semantic content of that feedback.
Oh. So the model was spending thousands of training cycles practicing how to be deeply analytical.
Exactly. By aggressively rewarding deep, deliberative reasoning tasks over and over again, the model's fundamental output heuristic shifted. It learned to be incredibly verbose. It wanted to show its work and think out loud for every single prompt.
And a benchmark like Trivia QA aggressively penalizes verbosity.
Exactly. If it asks for the capital of Spain, it wants the word Madrid. It doesn't want a 3-paragraph historical essay on the Iberian Peninsula. The model basically became too philosophical to win a pub quiz.
That is genuinely fascinating. It shows how profoundly the structure of the training environment alters the AI's eventual personality. There's also a hard systemic limitation to the COSE framework that we absolutely must highlight for anyone looking to implement this. The entire mechanism relies entirely on access to the model's logics.
Right. The raw, unnormalized predictions that sit right before the final softmax layer, which converts them into those token probabilities we discussed earlier.
So if you are working with an open weight model, where you have root access and can literally look under the hood at the exact mathematical probability of every single token being generated, COSE works brilliantly.
Yeah, but you cannot simply plug this framework into a commercial black box API.
Yeah.
If you are pinging a standard cloud model that only returns the final generated text string, the framework collapses.
Right, if you can't see the internal mathematical entropy, you can't calculate the confidence score.
And while a developer might theoretically try to approximate that confidence in a black box setting, maybe by repeatedly prompting the model with, "Are you absolutely sure about this answer?" It fundamentally lacks the fine-grained, token-by-token precision that makes COSE so remarkably effective.
So to pull all of these threads together, what the team at GMU and Amazon has proven is that the next frontier of artificial intelligence isn't just about endlessly scaling up synthetic data generation. It's about building structural self-awareness into the models themselves.
Absolutely.
It's equipping an AI with the mathematical humility to weigh its own uncertainty before it commits to altering its internal parameters. It's the difference between blindly believing your own hallucinations and having the capacity to say, hey, my internal entropy is spiking, I'm guessing right now, so let's not carve this logical sequence into stone.
It is a non-negotiable step towards sustainable self-improvement in machine learning. Because if we've truly scraped the bottom of the barrel for human-generated data, AI must learn to navigate its own training landscape safely by making the optimization process acutely aware of the fragility of its own feedback. COSE prevents these models from collapsing under the weight of their own generated noise.
Which leaves us with a final, slightly unsettling thought for you to explore on your own. If future, vastly more intelligent LLMs continue to self-evolve using this exact kind of token entropy to dictate the size of their own learning updates, could an AI eventually deduce how the mechanism works?
Oh, that's a terrifying thought.
Right. Could a sufficiently advanced model inadvertently learn to artificially concentrate its own probability distributions, effectively inflating its confidence tokens? Just imagine a neural network essentially gaming its own self-evolution loop, feigning absolute certainty on its outputs just to force larger, more impactful gradient updates to its own architecture.
We will likely need an entirely new diagnostic framework just to detect if that kind of metagaming is happening.
And when that research paper drops, we'll dive right back into the mechanics of it. But for now, just remember, whether you are a human student or a billion-parameter language model, the most vital thing you can learn is knowing when you are just guessing. Thank you for taking the plunge into the state-of-the-art Gen AI sources with us. We'll catch you on the next deep dive.